Okay, in here I'm going to talk about the rotational equilibrium. Okay, so now previously when we talked about equilibrium, we only looked at it from a linear point of view, right? Which means that all we said is that there was no acceleration, and that basically the net force is zero. Okay, it doesn't mean that it's not moving, but it just means that it's not accelerating. So that's what equilibrium is, right? So now we have to add to that. In order to have equilibrium, you have to have 6 dimensions, right? So you have to have, well, 3 dimensions for the linear stuff and 3 for rotation, because you can rotate in around 3 different axes, right? But you cannot have linear acceleration, and you cannot have angular acceleration. In those cases, if you have both of these conditions, you are in equilibrium. Now, I'm only going to address the static equilibrium for this video. We'll talk about dynamic equilibrium later when we do rotational dynamics, when we start to talk about when things accelerate or not accelerate or go at a constant angular rate. Okay, so for now, I'm just going to talk about static equilibrium, which means the forces are balanced, the torques are balanced, and there is no motion. So the condition is the net force must be 0, okay? And the net torque must also be 0. And whether we do it as vector or not, we'll think about that in a minute. So I made some examples here. Now I'm going to talk about this just using examples. So the first one is I have a platform, okay, supported by 2 strings, 2 cables. So I guess I could call this tension here tension 2. I can call this tension 1. This whole thing is 10 meters long. Okay, and this cable is about 1 meter from the edge, and this one is 2 meters from the edge. And I have a person standing here, and they are 3 meters from this cable here. Okay, and this person here has a mass of 75 kilograms. This board has a mass of 50 kilograms, right? And the question is, find the tension in each one of those cables. So now, how do we do that? Let me just make sure we're recording. Yep, we're good. Okay. So in order to do this, I'm going to pick one of these points of application of one of these forces as my pivot point. So, and that's arbitrary. That's really up to you. So if I pick this point here, okay, it means that if this cable breaks, we're going to see some rotation, right? We're going to lose that equilibrium, okay? So I could have picked the other one. It does not matter what you pick. Now I have to make a list or draw my forces that are involved in here. So I already have the T1 and T2, but I also have the weight of this person. So since they have a bigger mass, I'm going to tell them, I give them a big mg, and I have the weight of the board, right, which happens at about halfway here. So at the center of mass, which we'll talk about another time, mg. All right, so now let's, with this one as the pivot point or the axis of rotation, which means it's coming at you, let's make sure that we write that the counterclockwise torque is equal to the clockwise torque, because your net torque has to be 0, so those two have to be equal in magnitude, right? So now from here, let's see what T2 does, okay? From this point here, T2 is pushing up, which means he wants to go counterclockwise. So it's going to be T2, and since it's acting on a 90, and all of them are, we don't have to worry about the angle, which is a good thing. So T2 times the distance from this point here to here, right? So if this whole thing is 10 meters, right? And this is 2 here, and there is 1 here. I think this is 7, right? Okay, I hope you can see that. Equals, now, this the person and the board want to make the whole thing rotate this way, okay, with respect to this point here. If we pick this as the axis of rotation, they will make it go counterclockwise. But for now, the way we have it, they want to make you go clockwise. Okay, equals the big mg. Now, how far is mg or this person from this pivot point? It's always measured with respect to the axis of rotation, times 3 plus the lower m times g. Now, how far is this point from the axis of rotation? Well, from here, where my finger is, to the edge, that should be 5, right? And if you take away 1, that should be a 4. Okay. Now, if we do the math correctly here, T2 equals, T2 should be 607.14. Now, in order to find T1, I can do this whole process again by picking the point of application of T2 as my axis of rotation, which is basically coming at you and going into the board. Or I can use F net equals 0, okay, because it's static, it's not moving. So which means forces up altogether equals forces down, okay? And if you do the math correctly here, you should get T1 equals 642.86 newtons, right? Okay. So this is considered pretty straightforward. Okay. So let's look at another example. Just want to make sure I'm recording. Okay. I think we are. Yeah. Okay. Next example. Maybe a little bit more challenging, but not super hard. Okay. So you have, I don't know, maybe a table. Okay. Okay. And you have 2 supports down here. And this has a mass 4m and it has a length 4l. And then you're going to place something on top of it. That's a quarter. That's about a quarter. That's a quarter the size and a quarter the mass. Okay. And the question is to find how much of the weight does each beam support. So in other words, I want to find the forces here. So technically, these are normal forces, by the way, right? Okay. So, but for now, I think we can just call them F1 and F2. So that's how much support you just are provided. Okay. So this block here has a weight mg acting right from the center of it, assuming uniform density. And we're always going to deal with uniform density. So the halfway mark for the big piece is in the middle, so 4mg. Okay. Now let's do the same thing. So I think in here I picked this point here as the axis of rotation, as the pivot point. So let's see what we get here. So now if you notice, F2 is trying to provide a counterclockwise torque. So I'm going to say that my counterclockwise torque equals my clockwise torque. So F2 times, well, how far is the point of application of F2 from the axis of rotation? That should be just 4L. Okay. Equals both mg's, or mg and 4mg, they both go in trying to make you spin clockwise. So it's going to be mg, and here we don't have to deal with the angle, it's all acting at 90 degrees. And here, this one is half L from the end. If this whole thing is L, this is half of L, plus 4mg times, and I think from here to here should be 2L. Okay, now if we do the math here, we should get that F2 is 17 over 8 times mg. Okay, we just write in terms of mg, or 170 over 8 times the mass. Now to find F1, you just do F1 plus F2 equals mg plus 4mg, because now it's not moving linearly up or down. So if we do the math correctly here, after we substitute F2, we should get F1 equals 23 over 8 mg. And I think it makes sense that F1 has to be bigger because it has extra stuff close to it, close to the left, so it has to support more. Okay. All right. Third example. Okay, we're going to try to find the mass of a mirror stick, and that's pretty much what you're going to have to do in one of the labs. Yeah. Okay. So this is the 0. This is the 100 centimeter mark. So you're going to come to the 10 centimeter mark, and you're going to put an object on top there. And that object has a mass of 70 grams. Okay. This is 100 centimeters. Okay. Now we're going to put a pivot point at the 35 centimeter mark. And we're trying to figure out the mass of the mirror stick. Okay, so that's what we're trying to do. Okay, so this is my pivot point, and you're going to see this in the lab. Okay, so in order for this to be balanced, clockwise torques have to be equal to the counterclockwise. So here we only have the torque caused by this, and on the other side, right smack in the middle at the 50, we have the torque caused by the stick itself. Okay. So this is just going to be, I guess I can call this small m, and I can call this other one large m. Okay. So in order for this to be balanced, this mg times this distance, and by the way here, since it's in equilibrium, I think I can leave everything in grams and centimeters as long as I'm consistent. Okay, so mg times, I guess we can call this distance L1, I believe. We can do that, equals big mg L2. So this distance here is L2. All the distances for torque are measured with respect to the axis of rotation, because this wants to spin this way or this way, right? So the axis of rotation is coming out of the board. Now the mass here is 70 times 10. Well, actually I can cross out the g's. Now look, if you're finding the net torque or just torque in general, you have to be in meters and kilograms and all that stuff. But if you're just doing equilibrium, you can keep everything in grams or centimeters as long as you are in the same units. From here to here, it looks like it's 25 centimeters equals the mass of the stick times how far is it from the 50 to the 35. It should be 15. And the mass is going to be 116.67 grams. Let's look at another example, which I think the next two are going to be a little bit challenging. So stay with me. And this is basically number 23 in your packet. All right, so you have a ladder, you have a wall here. Maybe I should have made this bigger, because that's where we have enough room to work. So here is a ladder. Okay, here's the wall. Okay, and this is the floor down there, right? And here the question is asking, well, how far up the ladder can a person go without the ladder slipping? Okay, so the forces here, you have a normal force from the wall. I guess I can call it Fw. You have a force of friction from down here, and you have a normal force that I call N. And you have the mg right smack in the middle. So if you want to follow, you can go to page page, number 23, I don't know what page, and find it. So this is the mass of the ladder times G. And I'm just going to guess that this person is going to be up here. No reason. Okay? So I'm just going to say that they are up there, and their weight is mg, big mg. And, well, maybe I should just put some numbers here. Okay, so let me just put numbers here. Okay, so this is going to be 200 newtons, and this is going to be 600 newtons. So this will move quickly here. Now, I have to pick a pivot point, right? So I can pick either up here, or I can pick down here. I'm going to choose to, in the answer key on Haiku, I picked the top, I believe. But this time I'm going to change it to here. And I'll let you decide which way is better. I think the way I'm going to do it here in this video is better. And the reason for that is because when I pick this point as my axis of rotation, I'm technically getting rid of two forces that don't do any torque. So I'm going to pick this point here. So let's try this. This distance here is 5 meters. And the bottom distance is 1.2 meters. And if you do Pythagorean theorem, I think you can figure out that that distance is about 4.85 meters. That's going to come in handy. So now, let's look at the torque caused by F wall, which is basically also equal to the force of friction, if you think about it. Side to side, you only have the friction acting to the right, and the force from the wall acting to the left. Okay, so which means those two have to be equal. Okay, so the torque caused by this FW, I'm going to use another method to do the torque. If you recall in one of the videos, I said, well, you can find the torque by finding the distance between the axis of rotation and the line of the force. So in other words, finding this distance here, right? So that's going to be, and we're going to avoid doing that sine and cosine stuff, right? Which we technically already done, okay, to find this length here. So counterclockwise torque equals clockwise torque, okay. Which means F times this distance here, which is 4.85, that's the torque caused by F wall, right? Equals, now let's look at the torques caused by the other guys. Well, the 200, okay, is going to cause, so the line of force of the 200 is here. It's this far from the axis of rotation, which I think you can see clearly, or you can do the math if you want. That should be half of this distance, because this point here is at the halfway, the 5 meters. So I think I can just 1.6 here. If you don't believe that, you can do some similar triangles and figure it out yourself. Plus, I'm going to say 600 times x. Well, what's x? X being the distance between the marker is horrible. The distance between this line of force and the axis of rotation. So this green double arrow is basically your x. So I'm just going to put an x there, right? Now I think we can do more here. I know that FF is equal to mu Fn. Okay, so F is mu Fn, or basically I called it n here. Okay, and this is going to be the mu, I think, was given in the text, so that's 0.2. Now, the n, if you look at it here, n is the only force acting up, and you have the 200 and the 600 acting down. So that's 800. So I think we can change this F to 0.2 times 800, which is 160. Now, if you do the math here, you're going to find that x equals, what is it? Yeah, 1.094. 1.094 meters, right? So I can erase this stuff here. All right, so let's see how we can. So I'm going to try to figure out what this distance y is. That's what they're telling me to do. So I think I can do some proportions here, right? I can do maybe proportions between this triangle here and the one that's inside. Yeah, I think I could do that. So I can say, well, you know what? Y over x is the same thing as 2.5, okay, to 0.6. Okay, similar triangles, right? Yeah. I think here I did it differently. Well, I did it with the 5 and the 1.2, but it's the same thing, right? And I think you should get a y equal to, let me see. We have this number, which is 1.094. So that's going to be 2.5 times 1.094 divided by 0.6. We should get 4.56 meters. 456 meters. All right. Okay, one last example. The last example is going to be something like this. So you have a ring stand kind of support. Okay. We have, I don't know, maybe a rod here. Okay, and we have a string. So I'll do this maybe in a different color. So here is a string. Okay. And in addition to all this, just to make things a little bit more complicated, I'm going to hang a 900 grams mass in there. And that's going to be a meter away from this end, and this whole thing is going to be 4 meters. Okay, talk about complicated. This rod here is going to be 5 kilograms, and this angle here is 35 degrees. And there is some tension here. Okay. So two things I want to do here. I want to find that tension, and I also want to find the force exerted by this hinge on the bar. Yeah, that's what I want to do. Okay. So let's start with the tension first, I think. All right. So I'm going to do this with torque. The first thing you have to be careful with is this is 900 grams. So immediately make it 0.9 kilograms. Which means from this point here, you should have an mg of 9 newtons. Okay, 0.9 times 10. Okay. So I'm going to do the torque business here, right? So with respect to this point here, the T is going to give us a counterclockwise torque, right? So it's going to be T times this whole length, right? Which is 4 sine of 35. Just following the definition, because that's the angle between the lever arm and the force, equals, now the 9 newtons, right, is going to give us a torque that's going clockwise. So it's going to be 9 times, well, we're about 3 meters away. But the other thing we have to be careful with is that we still have the bar. We have to take its mass into account. So let's just use that. So that should be 50 newtons, 5 times 10. That should add up to the torque caused by the 9 newtons, because that's trying to make you spin clockwise. So that should be 50 times, well, how far is this point from here? That should be 2 meters. And if we do the math correctly here, I found a tension of 55.35. Okay, newtons, right? Now, I want to figure out the force exerted by this hinge on the bar, right? Now, I think this force should have definitely a horizontal component. And the reason for that, because it's balanced this way, so it has to have what I'm going to call an FH, horizontal component, to balance out with the horizontal component of T, okay? And it also should have a vertical component, so I'll call it FV, that will balance out, well, that if added to the vertical component of T will balance out the 50 plus the than 9. So that's what we have to do. Okay? So I think I can find this horizontal component easily. So F horizontal is just going to be T cosine of 35. And we already found the T, so that should be 45.34 newtons. Now to find the vertical component, I think I'm just going to do that vertical component plus the vertical component of T, which is T sine of 35, to start acting up. That should equal to 50 plus 9. Now the vertical component should be 27.25 newtons, right? Now you can probably see that this force is acting like to the right and up, but I think we can figure out that angle. So if I take it and I do FH here, and I put the FV here, I can figure out the force, okay, of the hinge. So I'll call it F, and I can figure out this angle. And you should be able to do that on your own because you have both of these components. So your answer should be for F, should be 52.90 newtons. And if we do it as a vector at 31 degrees, that angle is about roughly 31 degrees. And that's it. All right, see you later. All right, I'm out. Peace.